Okay, well, hello all, so I'll get started. So a quick recap, we were introducing a new definition of how we would measure security of a function family. So there's a few moving parts, so I'll just review that. The object whose security we are measuring is a function family, and that's simply a two-input function. The first input is called a key, the second some ordinary input, and these sets tell you from where everything is drawn. We have many examples, including any block cipher, such as DES. These games are used to measure security after we fix that F. Unlike key recovery, there are two games. Each of them exports a procedure called Fn. The name of the procedure is the same in both games, but it works differently. The adversary playing the games has as task to make queries here. It can make as many queries as it wants, look at the answers, and then decide if it was in this game or this one. The way the games differ is in the real game, when you call Fn on some input, it gives that input to this function in the second place, meaning that your x is a point in D. For key, it uses a key chosen at random inside the game and not given to the adversary. So you're getting outputs under a hidden key on inputs of your choice. In this game, F is not used. Instead, it's the random game. Whenever an input x is given to Fn, it simply returns a random point from this set. This code is to make sure that if you twice ask the same x, the second time you'll get the same answer as the first time, rather than a fresh value. The reason to do that is that was what would happen here. Since here you're applying a deterministic function, if you twice query the same x, you'll get back the same answer. So our adversary trundles along, and eventually it'll output a 1 to say, based on what I've seen, I believe I'm in this world, or a 0 to say, I believe I'm in this world. We're interested in how well it does at distinguishing, and that's captured by this advantage, which is the difference of two probabilities. The probabilities are of outputting a 1 in the real world and separately in the random world. Run the adversary here, compute the probability that that execution results in its outputting 1, and that number goes here. Run the same adversary here, compute the probability it would output 1, and put that number here, and the difference is the advantage. The bigger that is, the better is the attack, and the worse is the security of F. Okay, so this is what we played with. We saw examples of this, and where we left off was in applying the birthday problem to say something about PRF security of a block cipher. So there, remember that the birthday problem refers to the game of picking some number q of points at random from a set whose size is big N. And we are interested in the probability, called the collision probability, that within that space, two of them are the same. Another way of saying that is they are not all distinct. And what we know about that probability is that it grows roughly as q squared divided by n. So the number of points you draw divided by the size of the space up to some constant factors. Okay, so then that's where we left off. And now our question was, let's try to evaluate PRF security of a block cipher. That's a very general question, because this could be any block cipher at the moment, like DES or AES or whatever. You know its key length and block length L, and you know how it works, although we're not going to particularly exploit that. So I look at the games, and when I set F equal E, what will happen is that in the real game, replies will come from the block cipher under this key, and in the random game nothing has changed. They're just random points from the range set, which here is this one. And now again we put on our attacker hat and we say, how would I see some difference between these two enough to make a reasonably good guess as to which game is being played. So as an adversary, I make a bunch of queries to Fn. I look at the answers coming back, and something in them should give me some indication. There should be some structure that would give me a hint as to whether they're coming from here or here. Okay. Now, last time you already told me what the idea was, so we'll pursue that. The key thing is that no matter how you designed E, if it's a block cipher, then once you have fixed a key, the resulting function is a permutation on this set. What that means is whenever I ask two different x values, I have to get two different outputs. Now, I may not know in advance what I'm going to get because I don't know what key it's going to be computed under, but I do know that they will not be the same. But that property is not present here. Here I'm getting back random values, and random values with some probability will be the same. If I pick 1,000 random strings, there's nothing to say that they have to all be different. But 1,000 outputs of E sub k are mandated to be different. And that's it. So now what we're going to do is simply exploit that, and that'll give us our attack. Okay? So here's the intuition again. Whenever we build an adversary in these games, what we try to do is think, if I see outputs from Fn, what kind of difference might those outputs exhibit in the two games? And that will be something I can exploit. And it'll of course depend. Every time you have a different function family, it'll be different. But you look always for some structure. And here we know that the outputs will all be distinct in the real game. And in the random game, well, they may be distinct, but there's nothing to force that to happen. So that gives rise to the following strategy. So as usual, when you write an adversary, you do it kind of slowly, following the syntax rules. The first thing is you write the header. It says adversary and the name of the adversary. Then you know that you will have to query Fn. What this adversary does is it just takes some arbitrary q points from the domain of the block cipher or the block space. This q is a parameter of the attack. So depending on its value, the adversary will have a different advantage. And then for all those values, it just calls the Fn function. So it'll get back values like this or like this, depending on which game it's in. And now it looks at this intuition and says, how can I make a decision? So what this says is you expect them to be distinct here. So what it says is, okay, if they're all distinct, I'll think I'm most likely looking at a block cipher. So I'll bet 1 that says I think I'm in the real world. And if I find two of them that are the same, meaning they're not all distinct, then I will bet I'm in the random world. And that's it. That's our strategy. So we'll examine how well it does and play with that a bit. Okay, so any thoughts there yet? Yeah?
And just to be clear, PRFs, we are not interested in recovering the key.
Right.
It's about the randomness.
Right. Now, if you could recover the key, that would give you a way to violate PRF security. Yeah. But usually the point is that these other ways will be better. Okay. So the cleverness is in coming up with adversaries. Once you write one down, you will be needing to figure out what's the advantage. And that's usually mechanical, but it's good to go through with it, in particular because it checks your work. So sometimes, for example, what I've seen in quizzes is we ask you to prove that the advantage is as claimed, and people have an incorrect adversary, but somehow they claim it works anyway. And that's just not actually diligently going through the checks. So let's try to do it diligently here. So the way it works is we figure out the two properties one by one, starting with real. Here I've just copied the adversary and repeated the game. We're interested in the probability the adversary outputs 1. So we see when that happens. It outputs 1 into this condition, which means when all these are distinct. So now we ask, are they distinct or not? We're playing this game, and we know that the y values are coming out of this. So they have the value E sub k of x1 through xq. But we know, because E is a block cipher, that they will have to be distinct for sure. And so for sure our adversary will output 1. So we've killed that side of it. Now the other is a little more interesting. Notice that we don't change the adversary. It's exactly the same as before. What's changed is the game. So it still calls fn, it still returns 1 under exactly the same condition, but what these values are is going to be different. So now we say, is it true that they're all distinct or not? And we look at the game. And what we see is that what's coming back are just random values, which are L-bit strings. So what we're asking is, if I draw q independent L-bit strings at random, are they distinct or not? That's a question in probability. And if I'd given it to you raw, it might be a fairly difficult one. But luckily, we noticed that that's exactly what we studied. From the point of view of the birthday problem, it was exactly the question of drawing q random independent objects from a certain space and testing distinctness. And we remember that the collision probability is the probability that they're not all distinct, and so that they're all distinct is 1 minus the collision probability. How do we choose the parameters? Q here, because they're q things, and this is the size of the space from which they're drawn. Since they're drawn from this space, which has size 2 to the L, that goes over here. Okay. And so at this point we just have this formula, and at the moment we'll leave it like that. And now we'll compute the advantage, which is very easy. We just subtract the two probabilities. So we get 1 minus the collision probability, and then we get a quite nice conclusion, which is that the PRF advantage of our adversary is exactly the collision probability for throwing q balls into 2 to the L bins. At that point, we've done the analytic work. But now the next thing is to see what are the implications for security. So for that, we need some more numerical type estimates. So we go back to this fact we had, and it tells us that this probability is roughly q squared over 2 to the L. And in particular, it gives us this lower bound. It's at least 30% of that. So the conclusion now that's interesting is that if q starts reaching about 2 to the power L over 2, this starts getting uncomfortably close to 1. Now it's true it's 30%, but if someone breaks your system 30% of the time, that's not a nice thing to have, right? So from a practical perspective, 30% is not too different from 1. So what I observe is something like, once you have q input-output examples or q queries, you start completely breaking the block cipher. Now that's the conclusion that from a classical perspective is kind of novel and was not understood for some time, but is now pretty well accepted. Because if you go back to DES, what this says is you have a very good attack. So remember that the L here is the block length. For DES, that's only 64 bits. So 2 to the L over 2 is 2 to the power 32, and that's a feasible amount of computation. I'm not sure if I'd quite say your laptop could do it, but it'll get close. So, and certainly a well-equipped adversary with a good computer will find this really quite easy. So what that says is that we would at this point view DES as insecure from the PRF perspective, because this is a small number of examples needed to violate security. But what's more interesting is that when you move up to double DES and triple DES, which we remember strengthened DES relative for key recovery security, at least 3 DES did, it makes no change to this conclusion because the block length never changed. So in particular, 3 DES is no better than DES from the PRF security perspective. And that's part of why it got retired, yeah?
Why does PRF security matter if, like, most of your examples said you So you know like what scheme it's following, right? Like you know you're trying to like the encryption you're trying to break is using AES, right? Then PRF advantage doesn't matter, then, right?
So we'll have to look at that a little bit, but there is this. I don't know if I still have it. Yeah. So this, for example, is the practical illustration of why it matters. So these were attacks discovered a few years back, and they called it 32 because they operate on things like triple DES, which has a 32-bit block size. And they used exactly these attacks we just saw, but they actually recover data and information about messages over TLS. So it was a very practical exhibition of why those types of things matter. And as a result of this, triple DES was actually retired. So it's no longer standard. But it's a good point that it's not obvious from too many things up here. Where was I? It's not obvious from this attack that it has real-world significance somehow, because it looks like an abstract game. You have a real oracle or a random oracle. And it's going to take the next chapter to show us that you can make it practical. Okay, any other thoughts? Okay, so on the other hand, AES does pretty well. It's true that there's a dent because the block length is 128, so the attack takes 2 to the 64 time. But this is not merely computation. You have to gather that many input-output examples, and in the real world, it's not that easy to do that. And you can maybe rotate your key before you encrypt that much data. So generally speaking, people are okay with this at the moment. Okay, so now that we've understood what PRF security is, one natural question that arises is, if I hand you something like a block cipher, you have two different ways to assess security. In fact, you have three. You can ask about key recovery security, which comes in two forms, the target and consistent. Or you could ask about PRF security. And maybe you'll get different answers. So which are the things you should care about? One thing we have suggested is that PRF security is the ultimate thing. That's what we should worry about. But that raises the question that what if someone could find the key? That's obviously a problem, and yet PRF security never appeared to say anything about that. So the answer is that these are not completely independent, and there's a connection. And the connection is that if you know you have PRF security, then key recovery security is an automatic consequence. So you wouldn't have to ask whether this is present because it would be implied by this. Another way of seeing it is the contrapositive. If you give me a way to violate KR security, I will be able to violate PRF security. So for these reasons, once we have PRF security, nowadays what designers do is they just see that as the one attribute you need, and you're done with that. Okay. So now where does all this leave us? Well, we wanted to understand whether designs we have are good or not. And what conclusion we've come to here is the block ciphers we know, they are good in the sense that they seem to have PRF security up to the best possible limit, which means the birthday attack. Unfortunately for DES, that's not much. But still, it's as good as you could hope for, given that you have a 64-bit block length. And for AES, it's understood to be a pretty good PRF. We also looked briefly at CHA-20. There was a function family that's not a block cipher. And as far as we know, it has good PRF security. So what that means is if you're designing schemes or thinking about security and using any of these, you can factor all this in to think about what security you're getting. But one should also remember that anything like that is an assumption. To say that AES is a good PRF is purely an assumption in the sense that tomorrow someone may find an attack violating that, and that would not contradict anything mathematically. It's just that so far we haven't found them. Okay, so this is a bunch of exercises that one can try out, and next that's the end of that chapter actually. So it's simple enough. So any thoughts? Yeah. So you kind of want both, but the nice thing about PRF security is that it implies key recovery security. So if you have the one, you have the other. The caveat is then AES would only give you 64-bit security, and we think it has much more in terms of key recovery. But this connection is still a useful way to see things. It says they're not completely different. Okay, so then we would go on to the next chapter, which is so this has the title encryption, and that may sound a little bizarre because you may say, wait a minute, isn't everything we've been doing about encryption? And part of the purpose of the chapter is to argue that it wasn't actually. We hadn't quite got there because block ciphers are not how you actually want to encrypt data for privacy. But they will be an important tool to making it happen. And that's kind of the path that we're going to follow here. Okay, so my goal now is to design something called a symmetric encryption scheme. And its purpose is to take arbitrary data and encrypt it to produce ciphertext and provide privacy. But before we got to how you do it and even how you measure security, we want to say what is called the syntax, which is how do you specify it? If I have to write code or give you a mathematical description, what would it consist of? And our definition is that the scheme consists of 3 algorithms. It's a triple. Unlike a function family, which is one algorithm or function, here you actually have 3 of them. So what are they? First, there's a way to generate keys. This algorithm, if you run it, it takes no inputs, is randomized, and it'll pick a key of some size and tell you that's the key you're supposed to use. Now, most often this is very simple. There'll be some key length like 128. It'll just return a random 128-bit string. So not much going on there. The next algorithm is called encryption. It will take 2 inputs, this key and the message you want to encrypt, and it'll produce a ciphertext. But now we get to one of the more different and interesting elements of encryption compared to block ciphers, which is that this algorithm could be randomized. What that means is that even if you call it twice with the same inputs, due to internal random choices, it might return different outputs. So inside the algorithm, it'll call some random number generator and use that to determine its output. And we'll see that this is actually crucial. This is what Alice does to encrypt her data, produce a ciphertext, and send it to the receiver. And the receiver has to recover from the ciphertext the message. And there's another algorithm that helps do that. That takes the key and the ciphertext and gives you back a message. The symmetric aspect is that the key here and here are the same. You have to use the same one to encrypt and decrypt. And we do allow that decryption sometimes fails. So at times it'll say, something went wrong, I couldn't quite recover the message. I'll instead return this special symbol, which we call bot, to indicate failure. And that'll come up in some places. So note that these 2 algorithms, this is always randomized, this could be, and this is always deterministic. And that's something we'll have to understand why and how. But whenever you see a scheme specified or specified one yourself, you have to list all 3 of these algorithms. Yeah?
And so by randomized, can you like pick from a set of function families maybe? Like they're like, let's say like 3 block ciphers that you could have picked from, like 3 block cipher families, and then randomly picking from there. Is that what you mean by
So we'll see different ways to do it. Usually what will happen is there'll be one block cipher, but the input that goes into it you might pick at random, right? And somehow that input will not be the message. Instead it'll be some random thing, and that'll be used to encrypt the message. And we'll see why that's important and so forth. Okay, so this is more of a pictorial depiction of how you imagine the whole thing to be used. So once we've fixed a scheme, then the sender and receiver will have picked a random key and somehow agreed on it. So we assume that they have that key set up, and that's fixed for a long time. And now whenever the sender has a message, they run it through E and get a ciphertext using this key, and that's sent to the receiver. The receiver takes the received ciphertext and either outputs a message or this special symbol, and the receiver uses the decryption algorithm with the same key. The A here is to indicate that this is where the adversary sits, so it sees what goes across over here. Again, once you have the key, you imagine lots of different messages pushed through here and coming out. Okay, so before we get to security, we have to ensure that this provides sort of utility, which means that if everything is working as planned, the decryptor does actually recover the message that was sent, and that's called the correct decryption requirement. So what it says is that if I have some key and a particular message is encrypted, and that exact same ciphertext is decrypted under the exact same key, you will indeed recover exactly the message that was sent. So that's pictorial. The way we write it mathematically is this, and here we have to look at quantifiers. The quantifiers say this is to be true for all choices of the key that could be output by the key generation, and for all messages coming from some underlying space we call the message space. And for n, once you fix those two, it says encrypt the message under the key, get the ciphertext, and now decrypt that ciphertext under the same key, and I want to get back the original message. So very simple. This just reverses this. Why is there a probability around it? Because we said that E was randomized. So potentially what's coming back here has many different possible values. So there's some kind of probability associated with this. But we ask that it's 1, so it hardly matters. It just says always you will have correct decryption. What is this message space? It'll be our job when we give schemes to say what it is. So if I give you a scheme, I'll usually try to tell you, here's what the message space is. Yeah?
Did you just say in the previous slide that there are times when the decryption can fail?
Yeah.
How is that consistent with that formula?
Okay, good. So that happens. The purpose of that is when this C is not arising from this encryption. So it's arising from some adversary trying to send you something and getting you to decrypt, right? And we won't see that used for quite some time. So okay, so now we're going to get some intuition about symmetric encryption by looking at schemes. So we'll play with some example schemes, including very canonical ones that are routinely used. So I'll just recall a bit of notation pertaining to that. Since we will be using a block cipher or function family as a tool, we want to split inputs into blocks. And this notation does that for us. So you have some integer n like a block size. And if I take a string x and write this, what I mean is I've split it into blocks and let m be the number of blocks. I can only do this split evenly if the length of x is a multiple of this n. For example, 1 times n or 2 or 5, but not something like n plus 1. So that's assumed over here. So you can play with this, like suppose x is this 6-bit string, and I say split it into blocks of length 2, right? Then what would happen is that m would be 3, you would get 3 blocks, and the blocks would be exactly what you expect. First block is these two, second these two, third these two. If I take the same string x and ask you to split it into blocks of size 3, then again, as you expect, you would get two blocks, this one and this one, and you would have an m value of 2. Okay. Now, sometimes we want to index into bits of a string, and this notation tells us how to do that. So it pops out bits a through b of x. So for example, if x is this string and I want bits 1 through 3, then I'll get 0, 1, 1. If I want bits 2 to 5, 1, 1, 1, 0, 0. So just simple notation which you can pull up whenever you want. We're going to build symmetric encryption schemes from block ciphers or function families. And when we build such a scheme, as we've said, we have to specify 3 algorithms, right? Key generation, encryption, decryption. So let's start with the first. And the first in this specific case is very simple. If I have some family of functions E, let's say with some key length k, input length n, and output length l, then my encryption scheme will just pick a random key for this E as the encryption key. So that gets becomes a canonical choice. And we refer to these types of symmetric encryption schemes as modes of operation because they rely on some function family. Often E is a block cipher, in which case n equals L, but in some schemes it doesn't have to be. Okay, so this is our key generation moving forward. Okay, so now let's see if we can encrypt stuff. So given that we studied block ciphers, we have AES and so forth, and someone says go ahead and encrypt some data, there are natural ways you would do that. In fact, you would imagine that we already know how to do that. So what would you do? You know that you have this shared key and it's a key for the block cipher. So I just put my message into the block cipher, get a ciphertext, and that's my symmetric encryption scheme. So that looks okay. But then we start getting a few questions. The first one is pragmatically, this only encrypts one block, and a block for AES is 128 bits. But that's not what your data is. Your data could be a movie or an email or anything, a file or something like that, and it'll be much longer. So this doesn't work to encrypt messages of the length we like. So let's just view as our first task to just solve that problem. Doesn't seem like a very difficult problem. So with the idea that, yeah, it's not a difficult problem, what is the next obvious thing you would do? Well, that's depicted here. It's called electronic codebook mode, and that's a symmetric encryption scheme. So the way it works is it says, you want me to encrypt a long message consisting, let's say, of some number m of blocks. That's very simple. I'll just encrypt block by block. After all, I know that I can run my block cipher on one block at a time. So if I run it on each block of the message, collect up all the output blocks, this will be my encryption, my ciphertext. So a perfectly natural thing to do. Now, given that we said it's a symmetric encryption scheme, we may as well detail what that means. It means I have to tell you what the 3 algorithms are. So key generation, we already said, works like this. So we don't have to mention that. Encryption and decryption are written here, and that's how you usually see them in some kind of pseudocode. And they just implement the picture. So it says take the message, break it into n-bit blocks. Why n? Because that's the block length here. You get some number of blocks which could differ depending on m. Then you have a loop where for every block you run that block through E using this key over here and get a ciphertext block. You concatenate all the ciphertext blocks and you're done. But that's not enough. You have to say how you decrypt. So when you're decrypting, you have the same key and the ciphertext that looks like this. So you break that into n-bit blocks and let m be the number of blocks. And now to decrypt, you use the block cipher property that if you have the key, you can go backwards. So you run ek inverse on each ciphertext block, get back the message block, concatenate them all, and you have the message. Yeah?
So
Okay, so this is a good thing. There's actually two E's here. There's this E and this E, right? And they are different algorithms. This is the encryption algorithm of the symmetric encryption scheme, and this is a block cipher. They're both called E just because E connotes encryption, but they're completely different objects. So you do have to be font sensitive to tell these apart.
So in this case, you're just saying that the squiggly E is just the block cipher.
So whatever I'm saying is exactly this code, right? So I'm not choosing it or anything. It's an algorithm. Here are its inputs. Here's how it computes its outputs. So that's simple enough, right? Okay, you might notice that this is not randomized, and the reason for that is, well, I don't appear to need it. I've solved my problem. Okay. So, but now we start coming to the kind of realizations that with a little experience, what you're supposed to be able to get to, and which makes all this interesting, is I'm not going to claim that that was not a good method of encryption. And indeed, this is by now well understood, and it's viewed as a sign of really poor cryptographic literacy if you have built a product which has ECB in it. Anytime you see ECB, you're supposed to scream that that shouldn't be like that if you're ever analyzing a security system. So the weakness in it is very fundamental. It's not got something to do with exactly how the block cipher works, but just the fact that because it's deterministic, if you twice encrypt the same message, you'll see the same ciphertext. Well, of course you will. You have this message, you repeat it here, and since you haven't changed the key, the outputs will be the same. That's expected from this algorithm. But I'm now saying that this is not a good thing, that this actually is a problem. So why would that be true? Because now we start thinking of what we are actually doing with encryption and what kind of privacy properties we want. And as we start thinking of how we use it, we start seeing that stuff like this is not a good thing to have. So here's such an example. Suppose that you're in a situation where Alice is encrypting data and sending it to Bob, but everybody knows the context. And the context is that there are only going to be two possible messages, yes or no. So the simplest example is a vote. So Alice is casting votes on something, and she's voting yes or no, but the votes are encrypted for privacy. Maybe it's a simple command of the form buy or sell some stock. But whatever it is, the privacy requirement is exactly that nobody should know whether you're voting yes or no. It's not that they shouldn't know that you're voting. So everybody knows that you will be voting either yes or no. The only question is which. So let's consider that kind of setting under ECB. Well, first off, the encryption algorithm will simplify to just be an application of the block cipher. So why is that? Because here we will have m equals 1. So if m is 1 and there's only one block, then the script E sub k is just equal to the other E sub k on the full message, which is just one block. So we've simplified what encryption will look like. And now, as we observed before, it's deterministic. So we know that if two messages are encrypted, the same things are observed. So let's see what the adversary makes of this. So suppose that a couple of votes, M1 and M2, have been cast. Each is either yes or no, and they've been encrypted. And the adversary looks at the ciphertext, but it doesn't know the key, so it can't reverse the encryptions. It just sees these ciphertexts. When it sees the first one, it probably looks like complete gibberish. Assuming E is a good block cipher, it can't know from this whether the vote was yes or no. But this adversary is going to approach this differently. What it says is that, imagine, for example, that this was happening at a polling station, right? Every, whatever it is, voting day, you go somewhere and everyone casts a vote. And then your votes may be encrypted there and sent out to some tally center. So the adversary goes in early in the morning and casts its vote, and let's say it casts the vote yes. So yes will get encrypted and a ciphertext comes out. But the adversary observes this. So it sees this and it says, okay, I know the message was a yes, and that was the result. But now I want to know how my neighbor voted. So I wait a bit. And then the neighbor goes to the polling station and it casts its vote. And that, let's say, is M2 and gets encrypted and says C2, and your adversary sees this. And now I claim the game is up. So the adversary is now going to decrypt C2. Why does it do that? Even though it doesn't know the key, all it has to do is test if C2 equals C1. If they're equal, then M1 must equal M2 because this is a block cipher. And so that means this was also a yes vote. If they're not equal, this has to be a no vote. So a simple comparison between the ciphertexts will effectively completely decrypt this. And that happens even if your block cipher was extremely strong and your key was extremely long. So this attack has just bypassed the block cipher. Okay. So this is kind of an important observation which really takes us into thinking more about how security works. So any reactions to that? Yeah?
Also one more thing, like if you have a longer message, but you know that it's always divided into blocks, and if you figure out like the start or end of a message, and you can see those blocks, what they are, and if you see those blocks again, you can figure out what the message might be about again.
Yeah, you're right. Yeah, good. That's exactly right. Yeah?
It seems like randomness would only increase like the difficulty of guessing it or reproducing it by like a constant factor. It isn't really like this like end all be all. It seems like in this example, let's say there's like a set of possible like 3 ciphers for any message. You just need like a constant factor, more messages, and you can solve it.
Yeah, but we'll use a lot more than 3. So the way it's going to work is it's going to be an exponentially long number, and we'll see how to do that. But yeah, you're right. If it's a small number, it'll not change things much. Okay, so now often this picture is shown as an illustration of what happens with ECB encryption, which I think illustrates more the point he just made here. This is the penguin picture and image, and they took the file and they encrypted it pixel by pixel. But what you notice is you can still tell it's a penguin. And the reason that happened is that all it did is swap colors. So you can, the color itself changed, but this color is all the same and this color is all the same as in the original. So you can see from this that ECB is not doing much of a good job. Okay, so now if we want to go beyond that, the first objection may be, wait, it's just not possible. Why is it not possible? Because people's view of encryption is a code, and in that case it's going to be deterministic. And so whenever I apply encryption with a fixed key and message, I get the same ciphertext. If that's the case, our prior attack still works. Yeses are always encrypted to the same thing and nos to some other thing. And so it had nothing to do with the block cipher. It's a much more general attack, which effectively says any deterministic encryption scheme will fail. And at first that seems like quite a limitation, again because mostly people's view of encryption is that it is deterministic. But now we're going to shift that. We're going to think about encryption as randomized, and we also have now seen that it's necessary for security. So what will happen is the encryption algorithm, even with a fixed key and input, will do what we call flip coins. But that's an abstraction for saying it calls a random number generator or picks things at random from somewhere. The result is that even if you encrypt the same message twice, you most probably will not get back the same thing. So you can take an M1 equal to M2, run your algorithm, and it has enough randomness that even though with some probability the 2 ciphertexts are the same, that probability is going to be very small. And so collisions in ciphertext will tell you basically nothing. So that's the hope, right? But we have to see how we could make this happen. What are the challenges with making it happen? One of them is, how are we going to set this up so we can decrypt? Because what happens now is, given a particular message and key, there is a whole bunch of different possible ciphertexts an encryption algorithm could produce. In fact, it may be extremely large. There may be 2 to the 128 possible ciphertexts. But the decryptor has to know that all of them correspond to the same message. So we need a way for the decryptor to figure this out. So that's just one thing we have to solve to get there. Okay, so before we give solutions, however, it's good to kind of pause and appreciate the conceptual point here, which is that this is a departure from conventional notions of encryption. Both historically up to pretty much the 1980s, and cryptography existed, for thousands of years, and still in the popular mind, there's no difference between encryption and a code. Just like a substitution cipher, encryption is viewed as saying you have plain text symbols and you map them to cipher symbols. And those views always keep it deterministic. But now we're really changing that perspective. We're saying nothing like that works, and we want to do something completely different. Okay, so here's our first randomized encryption scheme. It's called cipher block chaining. The $ is to indicate randomization, and it's a mode of operation of a block cipher. So here I've fixed a block cipher, let's say AES, so 128-bit keys and also block length in that case, but you could make other choices. As usual, if I specify this scheme, I have to give you all 3 algorithms, and we already said how this works. It'll just return a random key from this space for which you can use E. So now how do we encrypt? Let's look at the picture first, or together. So when encryption gets a key and message, it'll break the message into blocks as usual, and let M be the number of blocks. So here we line up these blocks. Now we do process them with the block cipher, which we know is deterministic, but we have to infuse randomness somehow. The way that happens is encryption here will pick a random n-bit string. So remember, for 128 for n, so that's our random 128-bit string, and so that means there's a ton of possibilities, 2 to the 128. And that string is stuck here. Then that string is XORed with the first message block, and the result is pushed through the block cipher to get C1. All that uses this key. And now comes the chaining. That's what this stands for. You keep doing that. This gets added to the next message block. That gets enciphered with E sub k to give you C2, and you go on until you get the end. Okay? So this is your ciphertext. Now, one thing to note there is that this is part of the ciphertext. So here, when you look at the code, this part computes all of these, but C here includes C0. So the ciphertext here is 1 block longer than the plain text. Okay, so that's how encryption works. Now, before one thinks about security, the first thing is, well, can we decrypt this thing? And remember, the challenge for us there was that there are a whole number of different possible ciphertexts for a fixed message. So how does the decryptor know what the message is? Well, that's why we transmitted this thing over here. So what the decryptor does is it sees what it gets as a string of some length, and to break it into blocks, it first takes the first n blocks, which means it extracts this. So this is the whole of C, this is the first n blocks. It then takes blocks n plus 1 up to the end, which is the length of C, and that it breaks into some number of blocks, and we'll let m be the number of blocks with the block length always n. So this is just code for saying view your ciphertext like shown in the picture. Yeah?
I was thinking of another way to do this, like to save space, would be to base the random state on the encryption key and then make that generate the next random state. So since both of them have the same encryption key, they both will get the same random states, but the random states would still not be known to the random.
Yeah, but see, then they're actually not random. I mean, what will happen is once you fix the key, that state is the same, right?
No, but then you generate the next random state per block. But then since it's based on the initial random state that is the same for both the keys, all the random states that come after the first random state will be the same for both the encryption and decryption algorithm.
Okay, so but then you have dependencies across messages. So that's not something we want here. So here what you do is you want independent encryptions for different messages. And that first state then is basically your randomness, right?
First state is based on the encryption key. That's the random state.
So if it's based on the encryption key, it's not random, right? You need something different, freshly random.
But it will still not be known to the attacker.
But that doesn't matter because you still have determinism, right? And so those attacks will still work. So it's not a question of known, it's whether it changes or not. Yeah?
So for the algorithm, only the first C block is random?
Right.
And then for DK, what happens to the first C block?
Oh, it's used here, right? So when you decrypt, what you do is you take this, you go through D, and that gives you this, right? Then you add this, and you go here. And that's happening over here. So for example, when I is 1, you do EK inverse of C1, and then you add C0. So the C0 that's here is appearing here when I equals 1. The next time you take this, you get here through EK inverse, and you add this, and you get up here. So you notice that here, the EK is after the XOR, the EK inverse here is before the XOR. The XOR is outside. Okay, yeah?
The key that we're using for the block cipher is still being randomly generated, right?
It was randomly generated, but once that's happened, it's fixed. So you will now encrypt lots and lots of messages with the same key.
So then how do we share that between the person encrypting the message and decrypting?
So that at the moment is magic. So at some point we have to think about that. And again, if you want to think about it the way, for example, TLS does it, right now you're doing that is to use public key cryptography. But we haven't got there yet. Okay. So, so that was one way to do it, but so to build up kind of our example sets, let's give another way. Yeah?
So the first random state for any message would be the same in the previous one?
So these aren't states.
The first random number.
Yeah, the first random number, it's a string actually.
It will always be the same for any message?
No. So every time you call E sub k, there's a new choice, right? So all encryptions are completely independent, and each one of them makes a fresh choice. Okay, so we'll now give another scheme, which is actually more popular in practice at the moment. So some notation for this is that I want to take a string x and talk of something like x plus 1, x plus 2, etc. Like that, x plus 1, x plus 2. This is, let's say, an n-bit string like 128 bits, and I is an integer. So it's not clear what this would mean, but you can probably guess, right? What is x plus 1? Well, think of x as an integer, add 1, and then put it back in binary. So for example, if x was 1, 0, then what does it mean to add 1? I think of this as the integer 2, add 1, get 3, and then convert it to binary, and that's 1, 1. How about x plus 2? I take this, add 1, that gives me actually 4, but when I convert to binary, I drop the leading bit because I want to stay in 2 bits. So more generally, what it means is x plus I says convert x to an integer, do the addition with I, but do it modulo 2 to the power n, and then convert the result back to a string. But I mean, I think it's pretty intuitive. So, okay, so now here's a second encryption scheme. It also needs some starting primitive, but you don't need a block cipher. It's okay if it's an arbitrary family of functions where you don't have an inverse. In this case, the key length is k, input length is n, but output length could be something different from n. Normally, we would use AES, in which case L equals n, but you don't have to. So again, the key generation simply picks a random key from here, and we know what that is. So we're going to think how we do encryption. So it takes the key and the message, and it breaks the message into blocks. And we have to be a little careful here that the length of the blocks is this over here, not this over here. So it's the output length of E. Just like CBC, you pick a random string as the random choice, and this has this length n over here. And now here's how you encrypt. The idea is fairly different from CBC. What you first do is you ignore the message, you look at this value, and you increment it. You do +1, +2, up to +m, where m is the number of blocks, based on our conventions from before. Right? So you just, each of these is just think of as an integer, one more than the other. So these are all effectively constants, right? You run your cipher on those, and you get outputs that you think of as pads. So you get m such outputs. And only now do you use the message, and you just XOR it to those outputs. And those form your ciphertext blocks over here. Again, in order to allow decryption, your original C0 is put into the ciphertext. So the gray part is your ciphertext consisting of m plus 1 blocks, even though your message was m blocks. And that's called counter mode because this is the counter. It's incrementing by 1 every time. The $ stands for randomized. Yeah?
This looks like ECB a little bit. And then also, I feel like for these random schemes, if you know the encryption scheme, and then you look at the first, like that, let's say let's call it the random block, right? From there, it seems like really deterministic. Like, is that really like? I guess these are basic examples. They still don't seem too hard to break in the sense that.
Yeah, so it's true. It's a good idea to think of that as would that be a weakness? But it turns out these are good schemes. We'll see that in a pretty strong sense. In particular, if you try the types of attacks we had before, they don't work. But as you yourself noted earlier, it's important here that this is quite big. So it's 128 bits. So you can't easily like guess its value or something. But the fact that it's transmitted does not create a weakness. So the adversary knows it, and that turns out to be okay. Yeah?
What is the difference between like memory of the function and
So a block cipher is the special case where for every key, the map is a permutation. Right? So I don't know if I have that somewhere. Oh, great. Yeah. So here's the definition of a block cipher. So E is a family of functions, right? So that we already, that was what we started with. Some of those families are block ciphers, and that happens if whenever you fix a k, you get a permutation from D to R. Okay. So every block cipher is a function family. Not every function family is a block cipher. So in this particular case, I don't need it to be a block cipher. How is that visible here? You notice that in CBC, here we had EK inverse to decrypt, right? But here, there's no EK inverse used anywhere. So it wouldn't matter whether, yeah?
So EK across all the blocks are going to be calls, like different calls of the squiggly EK?
This E is this one over here.
Yeah, but like you see how like each of the blocks have a green like block?
Here?
Yeah.
So that's this one. This whole thing is this E.
Oh, okay. So that's like 4. Okay.
Okay. So now we should check decryption, and it's actually interesting. The interesting element of decryption is that we will not need to invert this E, which is why it doesn't have to be a block cipher. So the decryption algorithm knows the key, it gets a ciphertext, and the first thing it does is extract this initial block, and that's the first n bits. Okay, so this n over here, and it grabs that. Then it takes the rest, n plus 1 up to the length of the ciphertext, and that it breaks into L bit blocks, the L over here. And now it has all of this. Now what it does is it starts at the top here, just the same way encryption did, and produces the p values. It knows the key, and it knows C0, so it can add 1 and 2 and 3 and 4 and up to m, and based on that produce all these p values. Once it has those, it adds those to the C values and gets back the message. So here you just reverse the XORs. Okay. So the interesting thing there again is there's no E decryption needed. Right? It's a kind of nifty way of doing encryption. Okay, so this is basically the world's most popular way of doing encryption. So in some form or the other we'll see it many places. So yeah, you don't believe it works, right? Okay, so this is just to emphasize a few reasons people like it. One is that there's no EK inverse. The other is that encryption and decryption are parallelizable. So you can see that all these computations can be done in parallel because they don't depend on prior blocks to do the current one, which was not true of CBC. So on multi-threaded machines or with pipelined AES, you can do things faster. Okay, so now we should turn to security, and at some point we'll evaluate this in great depth. But at first we could start with some kind of sanity check. And the sanity check is to say, look, we broke electronic codebook mode and any deterministic scheme by looking at what happens in the voting application. So why don't we at least try that attack and see what happens? So again, let's go back to the setting where there's only 2 possible votes, yes or no. And your adversary has set the first vote to yes, and it knows the ciphertext. And it's trying to figure out what the second vote is, and it hopes to do that by comparing ciphertexts. But now say encryption is done with CBC. So when the yes is encrypted, a random initial vector will be chosen. That will be added here, that will be run through EK, and that will give you this. And the ciphertext the adversary sees consists of both of these things. It's a 1 block longer than its message. Okay, now it knows this encrypts a yes, and before at least there was a good deal of information. It waits for the second encryption of some unknown message M2, but with the knowledge that it's either yes or no. But when you run CBC, every time the algorithm runs, it makes a fresh random choice. So it picks this C2 independently anew at random from the space of blocks of the block cipher, and then does the same thing, adds it here, runs E sub k, gets this, and now our adversary sees this. So now our adversary wants to know, can I use these 2 ciphertexts to just check whether M1 equals M2? And the problem is it gets stuck, because if it thinks it can just compare them, the result will be they're basically never equal. Right? The chance that they're equal is like 1 × 10⁻⁴, which is infinitesimally small. So regardless of whether M1 equals M2, these are not going to be equal. It might think of something else. It might say, well, what if I only compare the second blocks or something like that? But that doesn't work either. So basically you play around with this and you start seeing that we really have done something. So this has circumvented whatever attacks we had. Okay, so so at that point we would get into more sort of serious security discussion. So instead, I guess I'll pause. And I was thinking that maybe a good thing to discuss again, because that seems to be useful, is actually to just talk about the homework rather than something too far out. Although I'll probably talk a little bit of something a little far out at some point. So let's go back again and think about the homework. So this is a PRF problem. And it says, I give you this family of functions called G, k-bit keys, L-bit inputs, and a parameter called R. And I define another function family, which is G to the R. It has k-bit inputs, but the k-bit keys, but the input is twice whatever it was over here, and so is the output. And then you have some code to define exactly how you compute outputs given the input, and you're asked to attack simple cases, G with a 1 and G with a 2. Okay, so what do you do here? Well, the first usual steps, right? Remember, as per the instructions in the how to approach problem sets, which you can always pull up again, the advice is work on paper. Don't go to the play crib, start working on paper. Next thing you would do is look at the definitions. So you would remind yourself what function families are, what PRF security is, and so forth. And then when you do that, you would see that you have these games, and you have to figure out how to play these games and win, right? So that's how you get going. Okay, so now, as I said last time, one of the ways you build up better understanding and deeper understanding is by the questions you ask yourself that are not here. So in that regard, can you think of any? Something that would help you, I mean, you might be curious about, is not asked. What could you ask? We went through this last time and you told me what you could ask. Yeah? But that's a little vague, so like what? Well, G is given to, okay, G is a family of functions, right? So what do you conclude from that? Right, so that means it could be or not be, right? So it's not, that's not going to help. Okay, anything else? What did we ask last time when we defined a function family? I mean, we just saw function families. What are some attributes they have? Yeah, but what I'm looking for is a new question that's not asked here. Not an answer, a question. So something you can ask which will enhance your, because the way you understand things is through this kind of process. If you don't ask yourself questions that aren't there, you limit the scope of what you're thinking about. So this is how you grow. You ask yourself new things. So when you have a function family, there's an obvious question. What's the question? Right, we just talked about function families. Yeah? Yeah, exactly. Thank you. So, and it's the same question we had last time, right? Remember we put up this F, and after a long time we said that. So now, I don't mean G, I mean this thing over here. Have you asked yourself if that's a block cipher? Like, that would be a good thing to ask, right? This is going to help you understand stuff. So, is it? This GR, what I've defined here. Is this too small? You have this code. Is this thing a block cipher? Right? So that would be a great question to ask yourself, right? And the best part would be that you thought of that and you weren't told to ask it. Okay, So now you can think about that, but let's ask another question. Does this thing look familiar? Have you ever seen this GR before? Did you try thinking about that? Is it coming from Mars or is it something familiar? Any thoughts there? Suppose, yeah?
Well, my question is like, is this kind of like the same way on DES is set up?
Okay, good. Yeah, exactly. So that was the insight over here. So I don't know if I still have, where I may have that. But yeah, so again, after going through definitions over here, you might remember that when we talked about DES, this is what it looked like, right? And here we have 16 rounds, and here's the picture, and here's the code. Does that look familiar relative to our thing? It's the exact same thing, right? Okay, and how do you match the two? So for example, what is R for DES? Huh? And go back to the algorithm. Oops. Yeah. So what is the R value for DES? 16, right? What is this G for DES? Yeah, it's the F, and you even know exactly how it works, right? Because it tells you here how F works. What are the little k and little l values? So key length here, L and L. So what are those for DES? Yeah, I don't know who said that, but yeah, 48 and 32, right? So if you had observed that on your own, I claim it would really help. So try to do this, right? So in general, whenever you, for example, again, like I said last time, often my goal is not to create problems just to torture you, that there's a point. And the point here is, this is DES actually you're looking at. So there's something to learn about that. So now you can interpret the problem. What is it saying in terms of DES? After all, it's telling you these are not secure, right? So what does that tell you from a DES perspective? Yeah?
Well, the thing that interesting here that is that DS is like hard because it's for I to 16.
For what?
Like DS there goes for like for I equals 1 to 16.
Exactly.
That's a big factor there for here, and that going to R makes it more exploitable. But like I don't know, like the DES analogy, like I guess can show you what bigger weaknesses in this algorithm, I guess.
So let's go back to what you first said, which is that you're doing from 1 through 16, right? So as you told me, the R value is 16, right?
Yes.
And what is it here?
1.
1 and 2. So that's the point, right? So what it's saying is you can't reduce that R value too much before you get into trouble. So if you got curious about it, what's the next question you could ask?
What does the equation look like if I plug in R equals 1 there and then look a lot simpler?
Well, along the path we're just saying, right? What you said is R equals 16 is DES, R equals 1 is bad, R equals 2 is bad. What's the next question? Yeah. And the most immediate thing after 1 and 2? What do you think would happen with 3? Right? So if you ask yourself and play with stuff like this, you're going to find the class really easy. You somehow find that everything I give you, you already know, because you've predicted it effectively. So try doing this game. So try playing this game of kind of asking yourself questions that are not there. Maybe you'll answer them, maybe you won't. But you'll get the context and the understanding that will carry further. Yeah, Alan, you were saying something I didn't catch. Okay, okay. Yeah. So now, in case you're curious, or do you want to guess, what do you think happens with r equal 3? Of course, this is a complete guess, right? So you can hazard a guess. Yeah? Yeah, interestingly enough, it is. So nonetheless, DES does 16, right? And the reason for that is that it's safe here for 3 only if G is very strong. And in DES, the F function is not that strong. So you need to do it more often. But that gives us some insight as well. Okay, so anything else about the homework? Yeah?
What do you see means strong for G? Like, wait. So, your definition of strong is just like you going through the sum of all the advantages. Is that what you mean?
So that's a good question, first off. It's good to ask. That's exactly the line thought. You're asking, what does it mean for it to be strong? The answer is it's a PRF. It has PRF security. And if you look at the DES function, it doesn't. It's pretty. So that's good. Yeah? How low an advantage? What?
With PRF security.
So as good as you can get, you hope for as good as you can get. Here it doesn't have to be a block cipher, so there's no birthday attack. So for G itself, you can hope to get, maybe that the advantage that it's as secure as key recovery. You have k bits of security if it's really well chosen. Okay. So I'll stop there then. Okay.
So what I was talking about, can you take a look?
Yeah, so you see, this is actually deterministic, so this will not work.
But for different messages, there will be different random states, yeah?
But the problem is at the beginning, it's the key.
Yeah, in the
So-
beginning it will be the case.
Yeah, that is not going to work.
But that's just for the first
Yeah,
first
so
block.
that block will that will already fail, and then you will.
Could you give me an example of how this,
Well, it's deterministic, right?
yeah.
Oh, you do have some randomness in here.
Yeah, so the first random state is
Mhm.
K, but after that you just cycle the random string back into the random state generator and you generate new random states. But the order
But
of
how
the-
is it used exactly? What does it mean to generate new ones?
like np.random, you can set the random state to any number you want,
Oh, okay.
like that. So there's like, if you set it to a state, it will give you the exact same answer again and again. So it's repeatable in that way.
Yeah, so then I don't know, because I don't know what this random generators do actually.